Hello, my name is Juan Pablo Gevaudan, and I am an assistant professor here at the Department of Architectural Engineering at Penn State University. Now, I am also the PI of the Responsive and Adaptive Infrastructure Materials Laboratory, or REAIM for short. Now, our research focuses on discovering the links between the chemistry of low CO2 cementitious materials and their properties and degradation performance over time. We study this link with experimental and computational tools. Now, you may be wondering, why care about concrete? Well, it turns out concrete is the #1 material used all over the world by volume. And here in the United States, we need about $588 billion to repair our aging infrastructure, which is mostly made out of concrete. Now, one component of concrete is cement. Cement is a binder that glues rocks and gravel, mainly, and sand together to create concrete, the material. Now, cement, and mainly the production of Portland cement, accounts between 4 and 6% of global CO2 emissions. Now, whenever we're studying concrete materials, there is many exciting challenges in the research component. Mainly, cement is a complex binder material. It is composed of multiple phases that act to glue sand and gravel and harden over time. Concrete materials actually have multi-scalar porosity, ranging from the nanometer range all the way to the centimeter range. Of course, again, this porosity changes over time because phases form over time in these pores. Also, the formulation for the cement, that binder, it is highly variable. And it's variable because we can create cements from waste products or industrial byproducts or even clays. Now, lastly, whenever we're thinking about concrete, we have to keep the construction industry in mind because they are the main users of concrete. So that means that our concrete materials need to be cheap, durable, and workable. These add many interesting challenges to the study of cement and concrete. Now, here at the REAIM lab, we have a vision. That vision is to achieve harmony between the natural and built environment with low CO2 cementitious materials. We also have a mission, and our mission is to create leaders that can conduct value-driven research excellently and collaboratively for civil infrastructure and users. The goal of our research is to create a unifying theory that can predict material properties as well as the performance of these materials over time. Now, with this unifying theory, we can actually revolutionize and transform engineering applications, such as sustainable 3D concrete printing, or even the corrosion of reinforced concrete structures, as well as the immobilization of nuclear waste, or even the design of new cementitious materials that we have never even thought of before. So with these applications in mind, we're actually searching for the answers to the following questions. In the fresh state, we're really interested in how can we even map the rheology of these new cementitious materials. Particularly, frictional forces between cement grains is actually really interesting and dictates how printable our 3D concrete printed structures actually are. And also, the link between the hydration reactions of different cements and their morphology actually dictates that rheology that is so important for 3D printing. So how can we link all these aspects together and create sustainable 3D concrete printing? When we're thinking about the hardened state properties of our material, specifically as they apply to maybe the immobilization of radioactive waste, we're thinking, how can we predict long-term material properties? And by doing that, how can we optimize their durability? We're also interested in thinking about how can we describe and predict the immobilization of agents that are harmful for our materials, such as radionuclides from radioactive waste. We're thinking about the degradation performance of our materials, such as a degradation of corrosion of reinforced concrete. We're really interested in how does the chemistry of the pore solution affect the passivation mechanisms of steel reinforcement. Specifically, what is the role of sulfides, nitrides, or even carbonates in that process? Also, how does the time-based changes of pore structure affect the transportation of these bad aggressors? Now, lastly, when we're thinking about the design of new materials, this is an exciting time to be thinking about this challenge. And there are many exciting questions in this last part of our research, such as how can we reliably understand the reactivity of different waste products from industry or other avenues that we can get them from to create cementitious materials that we have never really thought about before? Or how can we track the in situ evolution of our materials at the nano to micro scale so that we can understand how macro properties are affected? Well, hopefully with this information in mind, you have a little bit of a taste of what our research scope is and where our research takes us here at the REAIM lab. If you have any questions, I invite you to email me. My email is at the top of this slide. And I hope that I can answer all your questions and welcome you to graduate school here at Penn State. Thank you so much for your attention.